We're back. We'll start with today's recitation. Today's recitation is about network optimization, data manipulation, model architecture, and hyperparameter optimization. The things that we're going to cover in today's recitation, the theory part will be covered by Professor Diksha in his lectures. But this recitation mainly deals with all those techniques that you would want to know for your homework on P2. Yeah, we start with data creation. So as you all know, deep learning is all about having data. Large amount of data would be required for training all your models to achieve high accuracy, and also the model should be able to generalize very well. So that is why you need large amounts of data. So the higher the amount of data that you have, the better your model would perform. It is very often that the data collected is very noisy, or it would have unnecessary information that your model would not want to learn out of that data. So we implement techniques of preprocessing so that we are able to get a clean data set. So some of the data sets that are available are Cypher data sets, MS data sets. We also have the library speech that has been provided to you for your one feature. In certain instances, we will not be able to get data in such large amounts. So we go into techniques of data augmentation, where we are able to generate more data from the already existing data. So this makes our models more generalized. So sometimes we are not able to get the data from the limited data that we have. So we adhere to techniques of data augmentation, where we reuse the data that we have and apply certain augmentation techniques like flipping, rotating, scaling in case of images. And in case of speech, we have time masking and frequency masking that you would probably be using for your homework, basically homework 1, 3 and 4. You can see there are certain documentation that is available in the PyTorch, which shows you the various transforms that are available and supported by PyTorch. The first link will provide you data augmentation techniques for images. The second one is for all the audio augmentations that are available. Okay, so the other technique is data normalization, where the data set that we have various different scales for different features. So in order to have a better and faster convergence, it is always advisable that we apply data normalization to the data. So say why we would need data normalization is because data could vary. It could vary based upon the lighting conditions or the gain in the speech or distortions, or any kind of background noise that is present while recording the speech data set. So in such circumstances, we use data normalization. Some of the normalization techniques that are used are Z-score normalization, min-max scaling, standard scaling, and substitute mean normalization. All of these normalization techniques. The one that you would probably be using for your homework would be substitution mean normalization. So, in substitution mean normalization, we provide a computationally efficient normalization technique that is used for robust speech recognition. CMN basically reduces the distortion by noise so that we are able to extract robust features so that our model performs well and learns on features that are more important rather than learning from noise and other background variations. So, CMN reduces the differences between your test and train data set that are produced by channel distortions. CMN is able to reduce the differences in the feature representation between speakers and also partly reduce the influence of your background noise. CMN is going to be used in your homework 1 P2. Keep that in mind. Then, like most of you people would have encountered homework on P2 and you might.
Isn't substitution mean normalization basically like for normalization on the substitution vector?
Sorry?
Can you speak up?
Isn't substitution mean normalization basically score normalization on the substitution vector?
That is true, yes. Essentially, all you're doing is using the frequency domain or the substitution coefficients and normalizing them, subtracting the mean and dividing by the variance. Optionally, when you do it, you're doing substitution mean normalization. If you're not dividing by the variance, you're doing substitution normalization. Just a fancy way of saying, do it for speech recognition to remove noise from substitution coefficients.
So the homework on P2 is out, and most of you might have started off with your training and hyperparameter tuning. So one major thing that determines your accuracy in your homework on P2 would be the model architecture. So basically, you are going to run many application studies and then have different various architectures for determining your classification problems. So how do you get a right model architecture? So some of the useful techniques to know what architecture works best for a particular model would be to read papers, blogs, and some Piazza, like basically the medium architecture cutoffs, etc. would be published on Piazza. Through that, we give certain insights on how architecture will work and all of that. So, as Professor Diksha covers in his lectures, like why deeper and narrow models tend to perform better, it's basically because of network sufficiency. Some of the model architectures that are recommended for ablation studies in your homework on P2 would be the diamond architecture, where you increase the number of neurons in each layer and then gradually decrease it as you approach the outputs. And then the other one would be pyramid or the inverse pyramid architectures. And then we have a cylinder. Keep the number of neurons same in all the layers. And then you can have other weird architectures as well, where you can mix and match pyramid with cylinder.
These aren't really recommended in any order. You guys have to most likely, empirically test out different network shapes and see what works for you the best. As you know, learning this works. We still probably don't know why certain network architectures work the way they do for certain deep learning tasks or data sets. So it's going to be on you guys to try and test out different architectures and shapes of networks to see which works the best for your task, which is homework 1 we do in this case.
So while you're working with your homework on P2, you have to experiment with various possibilities in your architecture. The network shapes, like I said, you can use the pyramid, diamond, inverse pyramid, and other shapes that are available through papers or something. And then you can experiment with deeper layers. You can also experiment with wider layers. You can have varying activation function. Like you could use the reduced linear unit, leaky relu, sigmoid, relu, surplus or damage. And then there are certain optimization techniques, normalization techniques, like batch norm or dropout. We'll cover much of batch norm and dropout in the upcoming slides. So remember that there's a parameter limit while you're doing your homework on P2. You can try various architectures, but try to ensure that all your parameters lie within the parameter limit that has been provided. You cannot exceed the parameter limit. So the next topic would be hyperparameter optimization. So what are hyperparameters? Hyperparameters are explicitly specified parameters that control your training process. These are predefined hyperparameters before you start off your training. There's a difference between a parameter and a hyperparameter. So what is a parameter? Parameter is something that is internal to the model. They are like your model weights and your biases. Hyperparameters are explicitly specified before you start your training process. This could be your batch size, it could be your learning rate, it could be what your dropout probabilities, and various other hyperparameters. Then hyperparameters are usually set by some machine learning engineer, but parameters are something that are learned by the model through your training process. So why do we need hyperparameter tuning? One is to improve your model accuracy. So you change the learning rate or you change the batch size, the performance of the model would vary based on all of these hyperparameters. And we would want the tuning for faster convergence of the model. Say, for example, if you're using a larger learning rate initially, then it would lead to a faster convergence. And as you gradually start fine tuning your model, going to a smaller learning rate would help you achieve good accuracy. And starting off with a very small learning rate would increase your training time because your model would not learn. It would learn, but it would learn very slowly. So having a good hyperparameter leads to better convergence and also better accuracy, faster training time. Then we have constraints on our resources. Say our training time is very limited, or the infrastructure that we would have, the GPU compute resources are very limited. So in order to optimize for all of these, we would require hyperparameter tuning. And also, most necessarily, to reach your high cutoffs for this. So some of the examples of hyperparameters are the batch size. So batch size is basically we are trying to divide our entire data set into smaller chunks, and then we are performing gradient descent on each of these batches. So having a large batch size and having a small batch size has its own advantages. Like in the case of SGD, having a smaller batch size would help in faster convergence, but also having a smaller batch size would cause implications with batch normalization. So you're supposed to find a sweet spot between choosing a good batch size that does not have a trade-off between your convergence and batch normalization. And then we have the learning rate. As I mentioned, having a very large learning rate could lead to divergence. Having a very small learning rate would actually increase the training time, and also your rate at which the network learns would be very slow. So you can vary your learning rate and see what best suits for your models. And then we have scheduler parameters. So when we are training, we use schedulers. So basically, we would be using a step scheduler. That is, after a certain number of epochs, the learning rate is stepped down by whatever factor that has been mentioned. There's another scheduler that is the cosine annealing, where the learning rate is dropped in very exponential. in a cosine. Yeah. So in the form of a cosine. And then there's a reduced LR on plateau. This scheduler basically keeps monitoring a metric. So the metric could be your loss function, or it could be your validation or training accuracy. So if the loss function is not reducing, then the scheduler automatically multiplies your learning rate by some factor gamma and reduces the learning rate until your loss reduces. And the same can be used in the max mode, where if the validation accuracy or training accuracy is not increasing, or it is saturated, then the learning rate is furthermore dropped. And then we have dropout probability. Dropout is going to be covered in the upcoming slides. So basically, dropout is like switching off your neuron at the time of training, and with a probability of p. So this probability also is one of the hyperparameters. And then context. As you might have encountered in your homework on P2, we have certain amount of context prior and after the frame of our interest. So context also is one of the hyperparameters in your homework on P2. And then we have size of the layers, which is nothing but the number of neurons that are present in each of the layer, and the number of layers, which is nothing but the depth of how many number of hidden layers that you would want to incorporate in your model. And then we have optimizer. Optimizer is basically trying to tie your loss function to your model parameters. So your loss function basically gives you the terrain, but optimizer is the one which chooses how we need to traverse in such a way that we go in a direction of steepest descent. And then we have weight initialization. So weight initialization is one of the most important factors, because this weight initialization, if our model is not initialized properly, then it would lead to exploding or vanishing gradients. So we'll cover weight initialization in the next. And then for your convolutional neural networks, that is in your homework 2P2, the kernel size also matters, and your stride. Kernel size is basically the filter size, and stride is the number of pixels that one must move across to perform the next convolution. So weight initialization. So one of the main parameters that determine your accuracy would be weight initialization. So weight initialization would prevent problems of vanishing or exploding gradients, and also can result in faster convergence, and also you will be able to find a better minima. So some of the weight initialization techniques that you could incorporate in your homework 1P2 would be the Xavier or Kyming or uniform weight initializations. So Xavier is nothing but you're initializing the weights to plus or minus √6 divided by the number of fan-ins to your neuron and number of fan-outs to your neuron.
By fan in, fan out, we mean incoming and outgoing connections. So, and I think for Kyming initialization, it's just randomly sampling from a normal distribution with zero mean and 2 over the number of incoming connections. That's the distribution you'll be sampling from for your weights for Kyming initialization. There's more information available in the documentation that you'd be using for PyTorch, and you're free to explore any one of these that are suggested. I believe PyTorch initializes most regular layers with Kyming initialization.
Over to which?
Right. Okay, so learning rate, as you might know, is one of the key things that you have to optimize when it comes to hyperparameters, because that's really what determines how your model converges, right? Because it controls the weight updates that when you're doing gradient descent, right? So you're probably going to want to experiment with different learning rates and use a learning rate scheduler for your homeworks. And the choice of your scheduler will heavily determine the rate at which your model converges, rate at which your loss reduces. And the scheduler effectively changes the learning rate across epochs with a fixed schedule, like Swati was saying, you could probably use a step learning rate scheduler. That's one of the most basic fundamental ones to use, where you wait for a certain number of epochs and then reduce the learning rate by a factor. And you have more complicated ones like reduce LR on plateau, which essentially reduces the learning rate based on a certain metric when that metric starts plateauing or decreasing with a certain amount of patience. The patience determines how long you have to wait for a metric to plateau before you decrease it by a certain factor. Uh, so the graph here essentially shows you some examples of how learning rate schedulers work and how they exactly change the learning rate over time. And yeah, if you choose a large learning rate, your model might end up diverging quickly. If you choose a really small one, it might take a long time to converge, or it might, get stuck in a local minima somewhere. So you guys have to kind of experiment empirically and find out what the best schedule is. Moving on to what an optimizer is. So as we might know already, gradient descent is the preferred way to optimize neural networks and then update weights and learn uh, uh, parameters of a model. But how exactly do you train your model in practice, right? How do you change the parameters of your model by how much and when? So that's kind of where optimizers comes into the picture. So they tie together the loss function and the model parameters weights. So at each specific training loop, in your training loop, every iteration, you'd be calling optimizer.step if you've seen your starter code already. And what optimizer.step essentially does is use the gradients that are calculated from uh, the loss function, right? And takes a step with the specified learning rate or does the gradient descent update for you based on whatever optimizer you use. Gradient descent is kind of the black box. There are like more complicated methods built on top of it. Some of them obviously you know as stochastic gradient descent, Adam optimizers, uh, Adam W, AdGrad, RMS prop, sharpness aware minimization are some examples. These Adam, stochastic gradient descent, AdGrad, and RMS prop will be covered by the professor in more detail in a few lectures, but you're free to kind of explore what they do in PyTorch's documentation. They essentially kind of use some algorithm to control the weight update in some fashion with the learning rate, right? So the way they do it kind of differs. So the picture over here kind of shows you how exactly you know uh, different optimizers start off at some point and eventually end up converging to a specific minima. And stochastic gradient descent is one of the most heavily used optimizers. Adam converges faster, but stochastic gradient descent is set to generalize better. There's a lot of debate about this recently, but this is kind of the evidence we have so far. You can go and read about the debate. There's a bunch of papers out there that argue as to why stochastic gradient descent generalizes better. Some saying that it's not really the case, but some saying that it is the case. There's still a lot of debate going on about it. Uh, there is a suggested approach of initially using Adam and then switching to SGD. A lot of people use this. I've linked like a paper that can help you understand this, but it's probably out of the scope of this recitation to cover because we would need a lot of time. Moving on to some of the most important topics here, which is overfitting. I'm pretty sure some of you might have heard of this already, but when the model trains for too long on sample data or when the model is too complex, it can start to learn the noise in the data and end up having high variance, right? So when the model kind of memorizes the training points, basically that's when we encounter what is known as overfitting, because that doesn't allow the model to generalize to a test distribution that it has not encountered before. So to combat overfitting, what we use is a set of techniques that minimize the loss while also minimizing the weights, so that we don't let the weights go too small or too large. These techniques are often categorized under the name regularization. So L1 and L2 regularization, is the most common used form of regularization at the start. You just add an extra element to the loss function, which punishes your model for being too complex or just using too high values for your weights. And the parameter that controls this is the lambda parameter. This is also known as weight decay, as you'll find in PyTorch's optimizers. So L1 norm is basically adding a term that is the L1 norm of the weights multiplied by a factor of lambda. L2 norm is basically multiplying the L2 norm of the weights with a factor of lambda. Dropout. So as Swati was saying, essentially what dropout is trying to turn off certain neurons while you're training your network. right? So all the connections that are incoming and outgoing to that specific neuron are basically null and void while training. And the reason why this is really useful is because neurons that are turned off keep changing every time, right? It's not like you decide to turn off a set of neurons and then you stick with that. So because you turn off a random set of neurons with a certain probability at each training loop, what you're essentially doing is creating a bunch of subnetworks and training them in parallel, and uh, creating these co-adaptations between neurons every training loop, so that it basically becomes more robust and doesn't overfit in some sense, right? So the image right there kind of shows you how exactly some connections or some neurons are just dropped out with a certain probability. And if you keep doing this, you're basically creating a bunch of subnetworks, right? And all of those are getting trained, and then they become more robust to overfitting. Uh, Batch normalization. This, we're going to kind of give you a general overview, but the professor will cover this in more detail in the upcoming lectures. So essentially, this is a really successful technique for accelerating training and learning better neural network representations. The key motivation is what is known as internal covariate shift, right? So we assume that the training data, when we divide them into mini batches and we use them in training loops, we assume that they all come from the same distribution, but sometimes each mini batch can have a distribution of its own, right? So because each mini batch can have a distribution of its own, what generally happens is these input distributions get, when they get propagated across these neurons in very deep networks, uh, each neuron has to model a change in these input distributions each time. And basically this leads to poorer learning in some sense. So the goal of batch norm is to basically normalize and center these mini batch distributions and then shift them so that the model doesn't have to learn different input distributions for each mini batch. So this co-adaptation problem is what is being solved so that learning can be accelerated and convergence can be accelerated. Um, so batch normalization basically normalizes the layer input by subtracting the mini batch mean and dividing it by the mini batch's standard deviation, which is kind of straightforward. But if each layer is normalized, right, the weight changes made by the previous layer is kind of lost, if that makes sense. So obviously that isn't what we want to do. So in some sense, once we normalize, we have to shift the input distribution again so that we can scale and shift the normalized value after centering them to the distribution that the mini batch models, right? So this is kind of what batch norm does with two learnable parameters, gamma and beta. I'm assuming you guys would have kind of encountered these equations in homework 1, part 1. These will be explained more by the professor, but this is kind of the general idea of what batch norm does. So the mean and standard deviation are calculated for each mini batch. And then in testing though, we kind of maintain a running average of these mean and standard deviations so that we don't have to calculate the sample mean and the mean and standard deviation for the test data set, because that doesn't make sense. We do this only during training. The benefits of batch norm, basically it enables you to have a higher learning rate, right? And if you can have a higher learning rate, you're probably, able to take larger steps towards where you want to go. So convergence is possible faster in theory. So essentially the reason why this works is because we kind of normalize data. So we don't have extremely large gradients, right, in that process. So we don't end up diverging even with a little bit higher learning rate on average. Batch norm also regularizes the model because uh, as I said, now each neuron doesn't exactly produce deterministic values for each mini batch, right? So that's kind of how it functions as a regularizer. Some other techniques that you'd be using is early stopping, which is, to be honest, extremely straightforward. Just stop training when you see the validation score decreasing, where overfitting is most likely to begin. And gradient clipping, basically when the gradient is over a certain threshold, or whenever your gradients are over a certain threshold, uh, clip them so that it kind of doesn't go above a certain threshold and end up giving you exploding gradients, which is also kind of straightforward. You have functions in PyTorch that enable you to do gradient clipping. Moving on to efficient training and logging, this is going to be very critical for you in homeworks because, as you know, you guys have study groups and you have to be work to make the most out of homeworks. You guys have to be working with your study group, dividing your tasks among yourselves, do training in parallel, and then log whatever works, whatever doesn't work, and then share it amongst each other because you're free to do so within the course collaboration policy. Um, so one of the first things that are useful for you is to use mixed precision training if your GPU is able to use it, right? Uh, Essentially, what this mixed precision training does is combine floating point 32-bit precision and floating point 16-bit precision during training, while kind of achieving the same accuracy as floating point 32 training. It essentially gives you almost a 2x speed up, less memory usage, which also enables you to have a larger batch size, a larger model, and a larger input. So it is very useful if your GPU can do it. So please do look into it. It can really speed up your training times per epoch. So what about loss of information? The way we do it is we keep a master copy of the weights, right? And this is converted into floating point 16 during each part of the training iteration, during the forward and the backward pass, as well as the weight updates. At the end of the iteration, the weight gradients are converted back and then update the master weights. So that's kind of how it works. This is a piece of code that kind of tells you how it's done in PyTorch. So you initialize what's called a gradient scaler, and with what is known as autocast or torch.amp.autocast, that's what enables CUDA to essentially do floating point 16 precision. You use the scaler to scale the gradients and call backward, and then you step the optimizer also with the scaler, and then you update it for the next iteration. So those are the three blocks essentially. And there's more information in the PyTorch documentation. It is kind of straightforward to plug and play. So you should be able to do it fairly easily. There is one thing to keep in mind though, if you are doing gradient clipping, please go through the example on the documentation that specifically tells you how to do gradient clipping, because if you don't unscale the gradients before you do gradient clipping, you might run into issues. So as you can see, mixed precision training only works for some GPUs, not all of them. Tesla T4, V100 and A100 GPUs are what come to mind. It doesn't really work with a P100 GPU, so you might not get the exact same benefit. For those using Colab Pro, you might be getting P100s most of the time. But if you do get a Tesla T4, maybe try it out. The benefits, sometimes a P100 is faster, sometimes a T4 is faster with mixed precision. So you guys have to try it out. So weights and biases, you guys might have already encountered weights and biases in the starter code. We kind of provided a boilerplate template, ready for you so that you can start using it. And it is really the best tool for you as study groups, because what you can do is create teams under weights and biases, and each of you gets 100 GB of free storage to save models and whatnot, and any sort of metrics. So when you create a team under weights and biases in the homepage, you should be able to add yourselves, your study group over there, and then you would be able to see all of each other's runs and essentially understand how exactly whatever architectures you're dividing amongst each other, how exactly they perform, right? And that really helps you tackle appellation studies for homeworks in a much more efficient way, right? And we didn't know this back in the last semester when we tried it. So I would highly recommend using this. It really saves a lot of time. And if you need to understand more about weights and biases, you can refer to the recitation, which we released, which was Recitation 0. And it has way more than just logging metrics. You can do something like hyperparameter sweeps. You can save your models. I believe code for that is already in your starter notebook. But please try to follow it more than anything else, because it will really help you do all of the part twos in this course. These are some things to just keep in mind for homeworks in general. So don't spend time exploring all possible variations and for the architecture and hyperparameters yourself. This is kind of where you need to rely on your study group, right? You guys have to divide and conquer, and then set aside some architecture variations amongst each of yourselves, explore it, and then report performance. And that's kind of how you succeed as a study group. We used to spend basically every weekend working on quizzes or homeworks and then dividing work amongst ourselves as study groups. And that's kind of what helped us succeed in the course and have a much easier time. When you start doing things all by yourself, you might find the course load to be extremely overwhelming. So please do make use of your study groups and uh, uh, and rely on their support to tackle homeworks, quizzes, and etc. Spend some time discussing variations, like I said, spending time on a sample of the data set, right? So this is another useful tip. The data set for homework 1, part 2, as you might know, is kind of very large, right? So if you are training larger networks, maybe it takes a bit too long for you to understand how exactly the model is performing, or an architectural variation is performing, or a hyperparameter is performing. So maybe it's worth sampling a portion of the data set, or just taking a random subset, say 50% of the data set, or 20%, 25%, 10%, whatever it is. And you can kind of use that specific data set to uh, do architecture search or hyperparameter search, and then trim out the ones that don't perform really well, go ahead with ones that do perform really well on the subset, and try to generalize with it on the full data set. A huge portion of your time might just go into monitoring your Colab or AWS and just looking at your model perform, and then you might probably be doing other work by having the tab open most of the time just to see how it's performing. This was a very common situation personally for me, as well as some of my study mates. So we recommend starting early for this reason. So you really don't have to worry about wasting too much time on architecture search towards the end of the homework weeks, deadline weeks, and so that you kind of know what works well and doesn't work well early on. So you can just train on a few networks, or like a couple of networks at the end, instead of trying to do architecture search all in the last week. You will be provided with the medium cutoff architecture for your homework soon on Piazza, and you can use that as a first step to ensure you get to 70 points for those who haven't done it already. So besides obviously using all of these tricks, deep learning is empirical and experimental. So you have to be willing to explore different architectures and not dismiss anything that might seem wild, because you never know, it might work. So that's kind of why you guys have to spend a lot of time doing aberration studies. Remember to shuffle the training data set, but do not shuffle the test or validation set. You can have to choose the learning rate wisely, like we discussed before. Too large of a learning rate might result in the model taking huge steps. Divergence can happen. Too small, you might just be stuck in a local minimum all the time. Have a learning rate scheduler. Explore those schedulers. It's extremely useful, especially more so as you keep progressing down through homeworks. So for batch size, use as much as your GPU can handle. Larger batch sizes usually tend to have better performance. So because you have batch norms, you don't have to worry too much about batch size or increasing batch size. Ensembling is another topic. There have been a few posts already that have, I think, on Piazza asked about this, but you can train multiple models to see if. Oh, question? Yeah.
Previously, what would happen if I shuffle the test set?
Essentially, the issue is, the bigger issue right now, is to be specific, is you want to read the test set in the same order, because the submission on Kaggle evaluates your test set in the same order, right? And if you start shuffling your test set, or say even your validation set, you probably might not be able to evaluate your model performance in a consistent manner, because your model is seeing samples in a different order. So that's kind of why we recommend not to shuffle the test or the validation set most of the time. The training set, we encourage the model to basically not overfit to a specific ordering of the data, right? So when you're doing it for the validation set, you're not really looking for the model to generalize or like learn from it. So you want to evaluate performance consistently across epochs on the same ordering of data instead of shuffling.
Shuffling is not going to change that. If you have different test set points, regardless of which order you put it, you're ultimately having one.
It depends on say some. It can matter for some specific tasks, some data sets. Say if you have a continuous stream of recordings and you're dividing those recordings into different tasks, maybe the order in which you you know giving data to the model for those recordings matter. Depends on the task really, but essentially this is just a rule of thumb. You can experiment with it if you want. As we were talking about ensembling, you can train multiple models, right? But you do have a 20 million parameter limit, as you might already know. If you don't, now you have a 20 million parameter limit. So you kind of have to stick with that for your final overall network. So if you can train multiple models, say weak learners, and then have a majority vote during classification, you have to ensure that all of the parameters of those individual models still stick to the 20 million parameter limit if that's what you're going to be using as your final overall network. More on ensembling will be covered in an upcoming recitation, but this is just to give you guys a heads up that this is something that's possible. Obviously, a lot of people forget optimizer.0grad during training or torch.inference mode while evaluating. So this is just a friendly reminder to keep that in mind. We've basically written all of this out for you in the starter notebook, but for future notebooks, you might not be getting the exact same amount of code being written out and handed to you. So there's some things to keep in mind. Learning rate usually has to shrink in time for convergence. So think about a schedule that slowly starts decreasing the learning rate as your model starts to learn. At which point you start to decrease it is really the goal of the schedule. So using some helper functions to delete or release unoccupied cache memory is also useful if you often run into out of memory errors with your GPU. So the data loader usually has default settings with numwork as 0 and pin memory is false. You can run it with numwork is greater than 0 and pin memory equals true, but this might not really work for every use case, because if you're using Windows, for instance, you're forced to use numwork is equal to 0 for some reason, and for Colab you can start off with 4 or 8, but Colab eventually restricts your numworkers to 2 and then 1. Unfortunately, this is also why some students are getting some multi-processing errors, because Colab eventually restricts the number of workers. But yeah, yes, it is unfortunate. It is what it is. Yeah, if you're getting CUDA related errors, a really good tip would be to switch your code to run on the CPU instead, because CUDA errors really have a genius way of just masking out what's wrong with your code and just telling you there's a certain error for whatever reason. So if you have a CUDA error, a good suggestion would be to switch your code to your CPU and then run it, so that maybe you'll find out where exactly the error in your code is. Setting bias equal to false and layers before batch norm. This is again to do with some theory behind batch norm, but the reason why we essentially do this is because batch norm centers the data anyway, and in doing so, it kind of basically removes the point of a bias in a linear layer, and because it centers and then shifts with a learnable parameter of itself. So setting bias equal to false in the weight class before may be useful for you, because it might not essentially be a useful trainable parameter, but you're willing, I mean, it's up to you to explore that. You can go through papers or posts online and see whatever tricks or possible optimizers. Maybe there's new optimizers out there that you want to try. Maybe there's new architectures that are out there that have been recently released that you want to try. Feel free to try those, but you are limited to using linear layers for your one. And as you go through different homeworks, the amount of variations that you can try will increase. But for the purposes of this homework, you are limited to the usage of linear layers alone. And always remember, this is kind of rule number 1, checkpoint your model after each epoch. You don't want to end up training your model for 50 epochs and then realize you forgot to save it, and now you're not able to do inference if your Colab session crashed or your kernel crashed or whatever it is. So do save your model after each epoch. I believe the code right now also saves your epoch, also saves your model under weights and biases, or I think there's comments that tell you how to do it. So you can save your checkpoints in weights and biases as well. You have 100 gigabytes of storage, so I feel like it should be more than enough for the purposes of 4 homeworks. But if you feel like it's not enough, you can even try saving it in your Google Drive if you have that connected. So yeah, that's about it. So there are a lot of things to try out for homework 1 P2, and so spend a lot of time with your study groups, spend a lot of time exploring architectures, hyperparameters, and best. If you have any questions, you can reach out to me or Swati, and I'm opening the floor to questions now if you guys have any questions to ask about anything that we covered today.